So, what if I told you that one of the deepest secrets of the universe, how light, energy, and matter actually work, was hiding in a simple graph? Well, today, we're going to crack that cosmic code. And it all starts with a few simple lines.
And that's really the heart of it, isn't it? These lines, they came from a really straightforward experiment, but they held a secret so massive it would completely rewrite the laws of physics. They're like a message sent from the universe itself.
And that's the big question. This graph, it forced scientists to look at the world in a brand new, kind of scary way. It was proof that sometimes the biggest truths are just sitting there, hiding in data that just doesn't quite add up. Okay, so before we can crack the code, we have to understand the experiment that created it. An experiment with results so bizarre, so impossible, that it left the smartest physicists of the early 20th century just scratching their heads. You're not going to believe how simple the setup for this thing, the photoelectric effect, really was. You just take a piece of metal, shine a light on it, and then you measure the electrons that get knocked loose. I mean, it sounds almost laughably simple, but the results, they were anything but.
And right here, this is where things get weird. You see, classical physics, which saw light as just a wave, made some really clear predictions. So think of intensity as brightness and frequency as color. The old physics said a brighter light, a bigger wave, should smack electrons off with way more energy. But nope. Reality showed that a brighter light just knocked off more electrons, but their energy stayed exactly the same. And the real jaw-dropper? The energy of those electrons depended entirely on the light's color. It was a total, complete contradiction.
So in walks Albert Einstein. During his miracle year of 1905, he wasn't just cooking up relativity, he cracked this puzzle too. He said, hey, what if we stop thinking of light as this continuous wave and start thinking of it as a stream of tiny, individual energy bullets? He called them quanta. And each of these packets, or photons, carries a very specific punch of energy. This idea right here was the birth of quantum mechanics.
All right, so with Einstein's wild new idea in our back pocket, let's go back to that graph. It's time to decode this quantum fingerprint and see exactly how every little squiggle on that chart proves his theory was right all along.
First up is this thing called stopping potential. Sounds super technical, I know, but the idea is actually pretty simple. It's just how much energy you need to apply to stop the fastest electrons dead in their tracks. It's a direct measurement of how much kinetic energy they have. And here's the kicker. That energy depended only on the light's color, its frequency, not at all on how bright it was. This was the first piece of solid evidence for Einstein's photon idea.
Next, we've got the saturation current. Now that's just a fancy term for the total number of electrons flowing out. And this is where brightness finally mattered. A brighter light means more photons are hitting the metal every second, which means more electrons are getting knocked out. It's a perfect one-to-one transaction. One photon goes in, one electron comes out. Simple as that. But this part is maybe the most crucial point of all. The threshold frequency. What the experiment showed was that for any given metal, there was a minimum color, a specific frequency, and if your light was below that, nothing happened. You could blast that metal with the brightest red light in the world for a week straight and not a single electron would budge. But then, you hit it with even a dim little violet light and boom, electrons start flying. It's exactly like a lock and key. The photon's frequency is the key and it has to be just the right shape to unlock that electron. And this little beauty is the equation that pulls it all together. E here is the energy of the electron after it escapes. HF is the energy of the photon that hit it, F being its frequency, its color. And that little symbol, phi, that's just the energy cost to get the electron out of the metal in the first place, kind of like an exit fee. This one simple formula perfectly explained everything they were seeing on that baffling graph.
So, you see, decoding that graph did way more than just prove some new theory. It actually revealed three absolutely fundamental, kind of mind-bending truths about the very fabric of reality itself.
First, light isn't just a wave or just a particle, it's somehow, bizarrely, both at the same time. This is wave-particle duality, the strange and wonderful cornerstone of all quantum mechanics. Second, energy isn't some smooth, continuous thing. It comes in these little discrete chunks, or quanta. And third, the whole quantum show is run by a single, tiny, universal number. And this is that number. It's called Planck's constant.
and we call it h. I mean, just look at how absurdly small it is, but its value dictates the size of atoms, the behavior of particles, and pretty much why the quantum world is so wonderfully weird. It is one of the fundamental settings for our entire universe.
Let's just look at that relationship one more time. E equals hf. This tiny little equation is the bridge. It connects the particle side of light, its chunky packet of energy, E, to its wave side, its frequency, f. This thing unites two ideas that should be total opposites, the wave and the particle, into one elegant concept. It is the mathematical soul of wave-particle duality.
Now, this is not just some abstract physics lecture. Understanding this quantum secret has completely reshaped our world and led to technologies that you and I use literally every single day.
Seriously, every single time you see a solar panel making electricity from sunlight, you are watching the photoelectric effect in action. The sensor in your phone or your digital camera, it uses that same exact principle to turn photons into the pixels of your photos. Electron microscopes, ultra-secure quantum cryptography, all of it exists because we finally cracked the code hidden in that graph.
And that, to me, is the real takeaway. A massive scientific revolution, one that gave us a peek into the deepest nature of reality and enabled so much of our modern world. It all started right there, with a simple experiment and a graph whose squiggly lines just refuse to play by the old rules.
It really makes you wonder, doesn't it? What other simple piece of data, sitting in some lab notebook or a computer file right now, is just waiting for someone to look a little closer? What other cosmic secrets are still out there, hiding in plain sight, just disguised as a few squiggly lines on a graph